Hey there, in this lecture we're going to start with our machine learning section, and we're going to study about the introduction of machine learning. Machine learning is quite popular nowadays, and with the advent of powerful computational resources and more data collection techniques, we can use the algorithms that people have been working on since about 10 years or 20 years ago, and we can actually apply them to get something out of it. So let's start with the formal definition. What is machine learning? Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. Although when we say that it gives the computers to study the ability to learn, it's rather an abstract and broad term, because we've learned that we write programs that ultimately are converted into machine code, which the machine understands. So when we say that the computers are able to learn by themselves, we're talking about algorithms or programs that have particular, you can say, properties that we will study later on that enable them to learn. So rather than using computers, it's better to use a program or a machine learning algorithm. A computer program, so there's a second definition of machine learning is a bit more precise, a bit more technical, when it suggests that a computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T as measured by P improves with experience E. So let's just pause a bit and try to understand what we have just read. So it is telling us that a computer program, so now this is a much more precise definition. Now it's talking about a computer program. It's saying that it learns from experience E. Experience is defined by the variable E with respect to some task T. So it is saying us that by doing a particular task, a computer program is able to learn from the experience that it gained from doing that task. And there was a certain performance measure when it was doing that task, which is measured by P. So if its performance on T, so let's talk about the performance of T improves with experience E. So performance of that particular program on that task will improve as it will continue to do more and more similar tasks. Its experience will increase. So you can say that a computer program, after doing certain tasks, will increase its experience, and along with that experience, it will also improve its performance. So there's a difference between, let's go back in the beginning. So the question over here we should ask ourselves that why was machine learning invented in the first place? So there is a concept that is called traditional programming. Traditional programming goes like this. We study the problem, we write certain rules, we evaluate those rules, and we analyze the error, and then we reiterate the entire procedure. The idea over here that the rules we write are the code or the programming code. So if you try to imagine, the rules are something like if-else statements. So if you have a problem, you study the problem and you write code to solve that problem, that would be the rules to evaluate. So the question is, why do we need machine learning? Why are we not capable of writing rules by ourselves? To understand that more, we need to understand what traditional programming is. So let's talk about an example. Let's imagine you need to teach a computer or write a computer program to follow traffic light rules. We will write programs using the legendary if-else statements that we will write instructions that if the light is red, you stop the car and turn off the engine. If it is yellow, you start your car engine. If it is green, you go. So these three simple rules define the extent of our problem and enable us to write some efficient code that is sufficient to our current domain. So from this example, what you've just seen and understood that this problem requires simple rules and less number of rules. At the same time, it is easy to program since it is simple and the number of rules are less. So why do we even bother with machine learning? Well, considering this problem, you don't really need a machine learning code. It's not that you can't write it. There you can write it, but it's not really necessary considering this particular problem. So the real question is, why do we need machine learning? So let's talk about another example. Let's say you have a certain series of images and you need to write a program that identifies which type of action is being performed. We have walking, we have jumping, we have running as well. So we have three actions over here we need to identify by writing the rules. So how would you write the rules for images in this particular program? What are the rules? So even if we try to write them down, the question is, let's say, so if the right foot and the previous back foot, the distance between them is large, which shows that in the image the person is running. If it is small, the person is walking. But there are so many variations to that fact. Sometimes the distance cannot be measured between the 2 feet. Sometimes there are so many other features. So the question is, when we're talking about jumping, we can write rules for whether both of the feet are above the ground or not. But we're talking about images, and we were talking about distance between pixels in that image. So there is a lot of rules, so many rules. We need to first identify feet, where the feet are located, and if they are actually feet, we need to classify, localize, and then measure distance. So that is a very computationally expensive task, and that requires so many rules to write and so many computations to go on. So the question is, how can you write the rules, or how many rules do we need to write? The thing is, you can start going on, and every time you test your program, you might end up with a non-acceptable answer that is not really accurate enough. Due to the immensely large number of complex and large number of rules which are highly complex, which does not seem right and requires a lot of effort, and in the end you might not just get what you want, and the solution is not that scalable or robust. So this is where we have machine learning. So the trade-off between machine learning and traditional programming is simple. Whenever you have a lot of data and the problem you need to solve is rather complex, then you will write a machine learning algorithm and you will train that machine learning algorithm on the given data. So the trade-off is between the data and the number of rules you need to write. If you have a lot of data and the problem is complex, it's simple to just write a machine learning algorithm that can learn from that data, and its learning will ultimately enable to write rules. So you can look at it like this, that a machine learning writes those rules by itself after looking at the data, and it continuously learns from it to solve that problem. So considering this pipeline, you first study the problem, you train a machine learning algorithm on huge amounts of data, and after that you evaluate a solution, and if there are any errors, you re-evaluate it and go through the entire process. So that's why we have machine learning in the first place. It became more and more complex to write rules, infinitely many rules, into a complex problem and still not get an appropriate result. That's why machine learning helped us a lot when we realized that if I showed all those images of running, walking, and jumping to a machine learning algorithm, then it will definitely be able to identify, based on certain rules that it will learn from looking at the data, to correctly identify which type of action is being performed. So let's talk about the types of machine learning we have. We have supervised machine learning and unsupervised machine learning. Both of them are basically based on the type of data we have. And the type of data will ultimately decide the type of machine learning algorithms we use. So in a supervised machine learning algorithm, we have a data that is labeled by human annotators, or you can say it is a human labeled data. So the ground truth, or you can say the example we saw earlier, we had a human to look at those pictures and identify, because it is rather easy for us to look at things and label them, and that will be of the highest accuracy, of human accuracy. But it has been seen over the years that machine learning algorithms have been able to surpass human accuracy, and we will see how they've been able to do that. But so supervised machine learning is the one in which we have a labeled data set. So the unsupervised is the exact opposite. We have data that is not labeled, it is unlabeled data, so we need to deploy unsupervised machine learning algorithms to learn from that unlabeled data. So let's talk about supervised machine learning. So as we said, that a human labeled data set enables the machine to learn from that data. So the labeling of the data set is actually the necessary supervision we can give to the machine learning algorithm when it's during training. So let's talk about supervised machine learning. The formal definition is a type of machine learning which requires a human-labeled dataset which provides the necessary supervision during training an ML algorithm. So it's quite a smart definition because it has connected the human labeling part to the supervision, and the concept is actually linked that whenever the supervision we are actually providing the machine learning algorithm is through our labeling process. We're actually telling the machine learning algorithm what type of data or what it can probably learn from that data. So the machine learning terminology we have seen over here is what is training and what is a data set. Well, you can actually say that training is the learning process and a data set is the data frames and the CFC files we saw earlier when we were talking about pandas, and these are also images and depending on the type of problem. So you can say that a data set is something that is human refined. So you get a data set after you have collected lots of data, you have pre-processed it, refined it into one data set that does not have any noise, that does not have any missing values or stuff like that. It is the perfect form of data that needs to be fed to the machine learning algorithm without any further pre-processing. So you can say that it is the final form of a data that is about to be fed to the machine learning algorithm. So we have seen that data frames before, we have seen that the CSV files, the tabular data, and we can see if we want to understand in a much better way using different terminology is if we talk about rows, we can say that these are data instances and they represent data of one particular house. In this particular example, these are the house prices. So one row shows the data of one house and they are exclusive from one another. So the other important terminology we have in a dataset is called a label or target value, which in this scenario, in this example, is the price of the house. This is what we call the labeling part, which we do ourselves. And it is also called the target value because this is what the machine learning algorithm takes it as a reference and learns, because we feed all the information apart from that target variable to the data and we tell the machine learning algorithm, okay, so after processing this information you should get this value of the price. And as the machine learning algorithm learns and learns through various iterations, it understands that it needs to get better and better accuracy by moving closer to the actual price. And the rest of the columns, or you can say features, which is a more machine learning term, and from now on we will use this term features for the columns of the dataset apart from the target value column. That is what we call the label. So to understand features, dataset and labels, let's look at an example. Let's imagine you have a quiz and you need to solve that quiz. For the answers of that quiz, that will be called labels or the actual value. The question statements will be called the features, and the entire question set or the entire total number of questions, including the options as well, will be called the data set. Training an ML algorithm is just like solving questions and then comparing your answers with the actual answers or the correct answers. It's like self-assessing yourself, and you keep on repeating the process until you get most of them right. So whenever you're preparing for an exam or a test, you go through this, and it's quite a common routine for most of the students. You practice a lot of questions, you compare them with the correct answers, which is your performance measure, and you get to a point where you can measure your performance as you process, as you solve more questions. You self-assess yourself and you repeat the process until you start getting answers that are more correct or more closer to the correct answers. And this is what we call training, and the same concept is applied to training an ML algorithm. So it is a better analogy to get a better sense of what machine learning does in a broader context of things, in a better and more abstract nature of learning. So this is what we call training. Another concept of machine learning is about making predictions. So whenever you have completed training of a machine learning algorithm, it's time to put it into action and make predictions on entirely different values which the machine learning algorithm has not seen during training. So in order to have a better analogy and understanding, it's like after you have prepared yourself by a lot of practice for your test and now it's exam time. So after sufficient practice, now it's the time to test yourself for real. After giving the test, there are possibly two options. Either you pass or fail. If fail, you evaluate why it happened, solve the problem, and try again. If pass, then that's a good job. And the same process is applied to a machine learning algorithm. Whenever after training, we put it through a data set on certain values, or you can say certain instances which it has never seen during training, in order to test it. And the predictions it makes are either correct or false. But there is a certain accuracy to that. So it's not only pass or fail, but actually the percentage you get. Obviously, if it is less than 50%, it's very less and you need to train it again. And there are certain techniques to do that. But for now, let's just keep it simple. We have training and then we have predictions. So in order to revise what we learned is that we have a data set of practice questions and we train an ML algorithm on that data set, which is similar to solving questions and comparing with solutions. And then we solve the exam or make predictions. And this analogy will help you understand what is the entire machine learning pipeline. We get a data set, or we prepare a data set, we put it into the machine learning algorithm for training, and then we make predictions. And depending on those predictions, on the accuracy of those predictions, we evaluate what we need to do. Either we train the ML algorithm again, or we launch it and then monitor it. Okay, so let's talk about the type of supervised machine learning problems we face and the type of supervised machine learning algorithms we have for the particular problem. So we divide the supervised machine learning problems into two types. One is regression and the other is classification. The regression is the problem that deals more with a continuous data set. A continuous data type which would be in the form of, so the regression deals with a data type which is continuous. Like we saw in statistics, the continuous data types of numerical data. So regression deals with continuous data type of numerical data. Like, what is the price of the house? Now this is a regression problem, but you need to remember that when you look at a data set, you need to identify the type of problem by looking only the target variable. The target variable, or you can say the label or the target value. The other type of problem is the classification problem. Now this deals with a categorical discrete data type. It does not deal with continuous data, but actually categorical data, which can either be true, false, A, B, or anything that is exclusive from one another and does not have a continuous nature. It can be numerical, but it needs to be discrete in that fact. So we can take the problem of differentiating between cats and dogs. So you have, after looking at an image of a cat or a dog, you decide what is a cat or a dog. Now this is how we divide the machine learning problems into two categories: regression and classification. Regression deals with the target value or the label which is continuous in nature, and classification deals with the target value which is discrete in nature or has a categorical data type which is not continuous. So let's talk about regression problem. How do we decide after looking at a dataset that it is a regression problem? The target value, after identifying which it is, we look at it if it is a numerical variable or not. For example, price. We understand that it is a numerical data type, and we also know that this is a continuous numerical data type. So we come to a conclusion that if it is numerical and continuous, this is a regression problem. As for classification, we decide by looking at a target value and look at it if it is categorical variable, and it can also be numerical, but if it is numerical and discrete and there it is fixed in range, then we need to identify it that this is a classification problem. We can have more than one categories for a given problem. We can have as many categories as the problem needs, but the key point over here that they should be exclusive, and each label or each category only identifies one instance of the data set. Okay, so let's look at another classification problem. Imagine you have tons of email and you want to classify which of the email is spam and which of the email is not spam. So this is rather simple. We can attest that this is a classification problem because the result is either a yes or a no in terms of spam email or not spam email. So we will classify it. So what we will do is we will take lots of emails which will have spam and not spam, and they will be labeled. The labeled tells us that this is a supervised machine learning problem, and we will use supervised machine learning algorithms for it. And then we know that this is a classification problem. Now you know that we are getting to a point where we are learning more and more from the data by looking at the label and looking at the type of problem. After that, we will feed a machine learning algorithm with lots of images containing both spam and not spam, and with the help of labeling, we will supervise it to identify which of them is spam. Whenever a new email comes to your inbox, you will be able to successfully identify it as spam or not spam. Another thing I want to talk about in the regression problem is that there is constant progression. So whenever we plot the data of a regression problem, we will see that this is continuous in nature. So there is a progression, there is a visual progression you can see, which is towards upwards, and we need a machine learning algorithm to understand what would happen when a new instance value there is. So from this, we will have learned that the regression problems are continuous in nature and there are certain progressions to it. And from that progression, we will understand and learn the pattern of the data. That will ultimately help us in identifying new instances or new values and predict them accurately. Okay, so let's talk about unsupervised machine learning. Unsupervised machine learning is that when we have a dataset that does not have any labels. So the question is, if you have a dataset with no labels, can you have a machine learning algorithm ever learn from it? Because we have reached to the conclusion that our labeling is the supervision we give to the machine learning algorithm, is the reinforcement. It's like we are the teacher. The labeling part of is the human teaching aspect of the machine learning algorithm that somehow contributes to its learning. So what if we do not have a labeled dataset? How can a machine learning algorithm learn from it? So if you have an analogy of the student test practicing problem, the question you can pose over here is that, can the student self-assess and learn if the practice questions had no answers? So you have nothing to compare yourself with. So is there any way you can actually improve? Well, I'm not sure about students, but in machine learning, we have unsupervised machine learning that enables an ML algorithm to learn without any supervision ever. Unlabeled dataset is one without any labels, but it does still have features. So we need to come up with a way that we can extract information from those features and learn from them. We know that features represent information, and if we study these features, we will get more and more information. And then we can learn from that information and using algorithms such as clustering and anomaly detection. In clustering is what we do is that we group together features that exhibit the same characteristic. For example, different Netflix users can have similar preferences. So if you wanted to group together a lot of people who watch the genre of action and thriller, then you will get a group of people who watch one particular genre. So they can be characterized by one characteristic. The same goes for other types of examples as well. So the other algorithm we have is the anomaly detection. In this one, we have to detect an unusual occurrence of a data instance in the dataset. It's just like identifying an alien information, or in a much better way, you can say that identifying an outlier. But it's not just as simple as that. It is much more complex whenever we're talking about an anomaly, because it might be very hard sometimes to identify a feature that does not belong or that is showing some sort of anomaly in the dataset. For example, we have the credit card fraud detection based on amount spent. So we can identify if there is a fraud in the credit card transactions if you spend an amount which is rather unusual from your everyday transaction or the transactions you ever made over the past few months. So suddenly you made a very hefty amount of transaction to an unknown account, or maybe you spent a lot of money that does not align and does not correlate with your average amount of spendings. So in that way you can identify that anomaly. So these are two types of algorithms which we will be looking at when we talk about unlabeled dataset or unsupervised machine learning. So in an unlabeled data set, let's imagine that you have a training set in which there are different groups of people in Netflix that watch different types of shows. So when we talk about the hierarchical clustering, we can cluster these groups into separate groups into separate clusters based on their particular characteristics, and if you want to visualize it, this is how we would do that. And in terms of anomaly detection, this is what we would visualize it by plotting this entire data set. We would see that the anomaly can be visually seen, but this is only easy as far as we have two features. But imagine that we have about thousands of features in a particular data set. So the features, you should remember that these are the columns, and most of the time we have to identify anomalies in images. So in images, we will talk about later in deep learning that in images, every pixel is considered to be a feature. So if we have an image of, let's say, n by n, and the value of n can be ranging from, the maximum would be 1024 into 1024, so the total number of features would be the product of those two dimensions. So that is why when the number of feature space gets bigger and bigger, it becomes highly difficult for us to visualize it on simple plot.